Hey everyone, I'll hold the mic here. Thanks Luca for the intro. I think we're good on the mic. All right, my name's Seth, and I'm here representing Intel. Intel's sponsoring this, but I work for a company called Metis, which is a data science training company. And we do full-time 12-week immersive programs. You might have heard them called bootcamps. Ours is the only accredited one, so we sort of tend to elevate it above that, but it's a full-time program where people can come in, learn data science, and after that, go apply for data science jobs. And we also do corporate training, where we go around and do meetups like this and also teach companies' employees data science, basically. So that's the end of the advertisement for Metis. The rest of this talk will be on how neural nets work and how to build them from scratch using Python. So I know we have, at all these meetups, there's a wide range of expertises in the room. So quick question, so a show of hands. Who here, I promise I won't make you do it, but who here thinks they understand machine learning well enough that if I told you to come up here and give a quick 30-second explanation of what machine learning is, you could do it? Okay, cool, only about a third. All right, how about neural nets? Who thinks they could give an explanation of what a neural net is? Okay, interesting. I think maybe more people raise their hands on neural nets than machine learning, because I guess it's a more specific thing, so maybe it's easier to explain. How about deep learning? Probably the same hands as for neural nets. Who could explain deep learning? Cool, about the same people. Okay, good. That's, I think, about the level that is appropriate for this talk. So we'll dive in and talk about how to build neural nets from scratch. So first of all, why this talk? If you've started learning machine learning or started learning about this exciting field of neural nets and deep learning, you've probably seen tutorials from libraries like TensorFlow and Keras that teach you how to, copy and paste 15, 20 lines of code from a tutorial. It reads in a bunch of data for you. It feeds it through a model. Something magical happens, and all of a sudden you have an image classifier, or all of a sudden you have something that can translate languages. And it's really amazing, and that is a testament to the power of the open source community and all that. But if you're interested in what's happening under the hood, that can be a little bit frustrating, and you can come away wishing you had a little bit of a better mental model for what's actually going on with neural nets. And so this talk sort of attempts to fill that gap. And this basically, I started figuring this stuff out as I was trying to learn this stuff, and ended up writing essentially what I'm about to show you tonight to determine how neural nets worked. All right. So, by the way, another thing is we're on a little bit of a small screen here. There's going to be a lot of live coding in here. I can zoom in on the code. I'll do my best to make sure everyone can read it, but if you're sitting near the back, you might have a hard time seeing. You might want to try to slide up to the front. This code, by the way, is all on GitHub. The link was on the first slide, and so yeah, it'll all be available if you want to check it out on your own. Okay, let's dive in. So to begin, do we want to import TensorFlow? Nah, forget it. Okay, what are we going to talk about? So this is a version of a 90-minute talk I gave at ODSC a couple weeks ago, where I went through both how to build a basic neural net from scratch and then how to sort of do deep learning stuff. So I think we have about an hour tonight, so I'll get through all the neural net stuff, how to build a basic neural net from scratch, and then get through at least the beginning of the deep learning stuff. So first we'll just talk about, okay, if we wanted to do a basic neural net, one hidden layer from scratch, how would you actually do it? Step by step, what is actually going on inside a neural net? And why is the thing that's going on, why does it seem to be working? What's the math going on there? So we'll go over that tonight for sure in detail. Then we'll talk about how you can sort of transition that step-by-step thinking that we come up with during the first part, how you can transition that into actually building deep neural nets. And you'll have to sort of change the way you think about neural nets when you do that. All right, and we'll show that we can actually learn the MNIST data set. We can do image classification just with this step-by-step sort of approach. Okay, so if you've started to learn about neural nets, you've probably seen diagrams like this, right? A bunch of circles and arrows connecting the circles, and maybe even some curves that look like that, but okay, that's fine. well, what's actually going on in this diagram? So this is actually exactly what we're going to code up. We're going to code up a neural net that has 3 inputs, has 1 hidden layer with 4 inputs, and 1 prediction that we're trying to make. So we're going to actually make this very precise. Yep, that's what we're going to do. All right, so let's say that we have data like this. Just ran some cells there. And let's say our data ends up looking like this. We've got 3 features, x1, x2, and x3, just 1s and 0s, randomly generated features. And we've got y that's also randomly generated, 1 and 0. So there's some complicated mathematical relationship that exists between these features and this output. In other words, sorry, the math rendering sometimes gets messed up here, so you have to run these cells, so I'll be doing that throughout. There's some mathematical function, n, that takes in x1, x2, and x3 and returns the right value y. There's some function that exists there. So how could we actually figure out what that function is? Well, first of all, we can't just do this with logistic regression. So there are no parameters like b or beta, w1, w2, and w3, so that we could create a function that just looks like that and have it map certain values of x to 1, certain values to 0, etc. You can't do this with simple logistic regression. Why not? Well, you can't do this if you sort of read anything about neural nets and why they're used. Neural nets exist to solve problems where the space is not linearly separable, fundamentally. I mean, they can do much more complicated things than that, but just for the simplest example that you would actually need something like a neural net to solve, imagine you were trying to build a classifier that classified the light blue points from the dark blue points. And you just had 2 features, x1 and x2. And you couldn't linearly separate this. You can't draw a line anywhere in this square so that the dark blue points are on one side of the line and the light blue points are on the other side. You know, can't be done. So what could we do? Well, we could do something like feature engineering. We could, going back to this diagram, say, okay, well, if x2 is less than 0.5 and x1 is less than 0.5, then this is light blue, and we could go on and manually create some features and try to solve the problem that way. And that's basically what researchers in computer vision and lots of domains did before deep learning came along in the last few years. And the problem is, who really likes to do that? Who likes doing feature engineering? Who likes going in and manually trying to figure out what these intermediate features are that can ultimately help us with our prediction? That's not, well, it would be great if we could just have neural nets essentially do this feature engineering for us. So that's what we're going to try to do. All right. So we're going to actually build a neural net, and we're going to make a prediction using this neural net. So here's where we're going to get into the math and sort of how it all works. I'm going to go through it quickly. I'll let you sort of go back and you can review all the equations and see exactly what's going on, but I'll sort of go through the individual steps a little bit quickly so we can get to the deep learning stuff. But at a high level, what you should keep in mind is what's going on is we're taking input, we're passing it through a neural net, and we're going to end up with a prediction. We're going to end up with a number between 0 and 1. And we're going to make that prediction in a step-by-step fashion. And along the way, we're going to result, there's these intermediate quantities that are going to result. I'm going to call them A, B, C, and then P is going to be the final prediction. All right, so let's go through. So step 1. Oh, these equations are messed up. So step 1, we want to take our original features and we want to create these intermediate or hidden features that are linear combinations of our original features. So some combination of our original features creates these intermediate features. So in other words, for each intermediate feature, let's say there's one called A1, we want to make it a linear combination of our original features. So just x1 times some weight plus x2 times some weight plus x3 times some weight. And similarly for all our other intermediate features. Yeah, I'm not going to do a bias in this neural net. It turns out we don't need one. But yes, great question. We would want to use a bias in a real neural net. A concise way to express this idea of intermediate features being linear combinations of our original feature is to represent those original features as a vector, and then represent the weights as a matrix, and then represent turning our original features into our intermediate features as a matrix multiplication. So I think this is an important point. There's lots of matrix multiplications that are going on in neural nets, both in the forward pass when we're making our prediction and in backpropagation when we're going to go backwards, and, well, we'll get into what that is. There's no sort of linear algebra theory here. Matrix multiplications are just a concise way of expressing that the features that are in the next layer of the neural net are linear combinations of the features in the prior layer of the neural net. Matrix multiplications happen to be a convenient way to transform one layer into another. But just because you hear the word matrix, it doesn't mean sort of linear algebra is going on here. All right. So coding this up, just define our original data as a vector there, and define a little weight matrix, randomly initialized. There's a whole science as to how these things are initialized, but for now, just randomly initialize it. And we'll just do a dot product of these, matrix multiplication, and get our intermediate features, sort of unnormalized. And let's go over where we are. So we just went from our original features to the beginning of our hidden layer. Okay, now what are we going to do? Now we want to feed these through an activation function. What are activation functions? Some of you, this is review, but it turns out that at each layer, so neural nets are these series of mathematical transformations that you do to data. It turns out you want to alternate linear and nonlinear transformations of data when you do a neural net. And the reason is, the actually fundamental reason is that if you just did linear transformations, the linear combination of a linear combination is just a linear combination. So in other words, if you took 3x plus 8, and in for x, you plugged in the expression 4x plus 7, when you did that math all out, you would just end up with some new expression that was ax plus b. So if you just did a series of linear transformations through your entire neural net, you would just end up with a big linear transformation, and it wouldn't be able to learn nonlinear relationships. So that's why you have to add these nonlinear functions in the middle of the neural net. So a simple, easy to understand nonlinear function is this sigmoid function here. Takes a number x and maps it to 1 over 1 plus e to the negative x. Maps small numbers to 0, maps large numbers to 1, it maps 0 to 0.5. So we can just feed those intermediate features we computed. We can feed each one of those through the sigmoid function, and each one of those will end up with a quantity b. And let's do that. Yeah. Yeah, feel free to. Cool. Good. Yeah, this is all on GitHub. This is in a, so who here uses Jupyter notebooks, really quickly? Awesome. Who here uses Rise to present from Jupyter notebooks? Nobody? Who here's heard of Rise? Only 2 of you, okay. I think this is worth it. So Rise is a framework that, no internet. Oh, I'm not actually connected to the internet. That will mess me up later on. What's the Wi-Fi? Oh, nice. Cute. What's the password?
Capital, so the password is R, capital R, exclamation point.
There we go.
Exclamation point, perfect.
Great. Okay. This Rise thing will be worth it, I promise. And connected. There we go, great. All right, so Rise is a Jupyter notebook extension. Who here has installed some Jupyter notebook extensions on their Jupyter notebooks? If you haven't, I'd recommend checking those out. That will make your Jupyter notebooks be able to do all kinds of cool stuff. Rise is a Jupyter Notebook extension that lets you create presentations like the one I'm using from a Jupyter Notebook. So I am literally running a Jupyter Notebook in my browser right now, but I'm using this JavaScript extension that lets me do all this presentation stuff with it. So we use this at Metis for teaching all the time. I mean, basically I'm doing like a PowerPoint presentation, except I have actual code running in it. So especially for those of you that are teachers, who here is a teacher? Who here like teaches stuff? Okay. Well, Luca, you should use this for teaching. All right, back to the neural net stuff. So we fed the input to our hidden layer through this sigmoid function. All right. And now we want to take these, let me go back one. Now we want to take the result of this and feed it through, or take a linear combination of these features and use them to make what's ultimately going to become our prediction. So we can do another matrix multiplication, another linear transformation. So we're going to create this quantity C that's a linear combination of the 4 B quantities we just computed. And the weights that result, I'm going to call W. So A, B, C, and P are the quantities, and V and W are the 2 weight matrices I'm using. All right. So basically, we could write, the point here is we ultimately want to do a linear combination, but we can write this conveniently as a matrix multiplication. So if we initialize our weight matrix here, and then do that dot product, that gets us our sort of unnormalized final prediction, this number negative 1.01. Then, so that's where we are. We've gone through that step, and now we're almost to our final prediction. And for our final result, we just want to feed that through the sigmoid function again. So let's just code that up. Let's feed this through the sigmoid function. And we end up with a final prediction for this neural net. So we've gone through step by step, and given the input that we gave this neural net and the weights we gave it, we have a prediction of 0.27. All right. Cool. That's where we are. And now let's compute the loss. Again, I'm using a loss function here so loss, what is loss? Loss is how much we missed by. All right, and that's what's going to tell the neural net ultimately whether it's doing well or not so well. I'm using a loss function here that's really easy to deal with mathematically, mean squared error loss. So it penalizes you equally whether you miss high or low, and has a nice easy derivative, which is important as we're going to find out. And I'll just code this up. So that's the loss. We missed by 0.27, as it turns out. All right, now we've computed our prediction and we've computed the loss. So now here's where the real magic starts. Now what? Great, this neural net is a thing that can take an input and make predictions. Okay, how does this thing actually learn? Well, here's what we want to do. Here's how to make this thing actually learn. We've made our prediction and computed our loss. And remember, each step in our neural net was just a mathematical function that was applied to some input and resulted in some output. So if we write out what we did in terms of mathematical functions, we could write it as this. We took in input and a weight matrix V, resulted in this. And we fed that through another function. We fed that into another function along with another weight matrix, et cetera, until we got our loss L. And we could write that as this. Just one big long function that has our input X, our weights V and W, and results in some quantity L. All right? So what do we want to do to make this neural net learn, or make this series of equations appear to learn? Well, what we want to do, as it turns out, is do this. We want to take every single weight in the weight matrices V and W and update them according to these equations. Basically, if an individual weight, well, I'll talk about why these equations make sense on the next slide. So, why do those equations make sense? Well, for those of you that are familiar with gradient descent, these are basically the gradient descent equations. But let's think about these for a second from first principles. So, if an individual weight, if increasing it causes our loss to go up. That's bad. That means we want that weight to go down. And it turns out that's what this equation does. The partial derivative of the loss with respect to the weight will be a positive number, so we'll be subtracting a positive number, so the value of that weight will go down. That's good. Now, what if increasing one of our weights in our network causes our loss to go down? Well, that's great, actually. We just want to keep increasing that weight. So that's what this equation will do. The partial derivative of the loss with respect to the weight will be a negative number, and we'll be subtracting a negative number, so this weight will actually increase. So this is what we want to compute. We want to compute this quantity here, the partial derivative of the loss with respect to all the weights in the network. All right. And how do we actually do this? Well, we know that the loss is just this quantity here. Well, mathematically, it's that. It's a big result of applying all these functions to both our weights and our input. And the magic of neural nets and the way the sort of math that makes them actually work is this. We can compute how much we need to increase or decrease each individual weight in the neural net by computing all these individual partial derivatives, which, remember, are just results of those simple functions that we applied during the forward pass. And then the chain rule tells us that if we just multiply them together in the right way, that our loss will actually increase or decrease, or our weights will be updated in the right direction so that the loss actually decreases. And this is sort of the magic of why neural nets work. So what we're going to do is go through now and compute all of these partial derivatives. This is, again, going to be a lot of math and a lot of sort of step-by-step stuff. But you'll see that when we compute all these, when we multiply them together, and then when we just repeatedly update the weights according to these computations, that the neural net appears to learn. So let's go through how these partial derivatives work. And you'll see that some of them get a little messy, but a lot of them end up being pretty simple. So first, the partial derivative of the loss with respect to the prediction. Well, remember, the prediction was just the loss as a function of the prediction was just this equation here. So the partial derivative of that with respect to p is just, as it turns out, negative y minus p. So coding that up is pretty easy. Coding that up is just that. That's our first quantity in backpropagation. Step one is done. And so that's where we've gone. We've taken our loss and we're going backwards. Questions so far? This is the idea of what we're going to be going through. Make sense? Cool. All right. So the next one is the partial derivative of this quantity c, which was the input to the final sigmoid function as it relates to p. But remember, since this is just the sigmoid function has this really nice property that if this is the sigmoid function, the derivative of this with respect to x, it turns out, is just the sigmoid function times 1 minus the sigmoid function, as it turns out. So that makes things nice and easy for us. So if that's how c gets transformed into p, then the partial derivative here is just sigmoid of c times 1 minus sigmoid of c. And that's easy to code up. There it is. All right. Let's keep going. Here's where it gets a little more complicated. Let me go back. And here's where there's actually a cool linear algebra theorem that shows in general why what I'm about to show manually, why this works in general. But this is where it gets sort of surprisingly, it looks complicated, but then it ends up being simple. So we want to compute basically how much each of those weights, how much changing each of those weights affects that quantity c. And remember that each of these weights, that c is just a linear combination of these weights with the input or the output of our hidden layer b. All right, so it's the result of doing this. Well, remember though that by the partial derivative of c with respect to w, we really just mean how much each one of these individual weights affects that quantity c, affects the thing that we're putting into the next layer. And it turns out that each of those is really simple. Yeah. Turns out that since c is just a linear combination of the weights with b, then the partial derivative of this c with respect to the first weight is just b1, since the partial derivative since the first weight isn't in any of these terms. And the partial derivative of c with respect to b2 is just, the partial derivative of c with respect to the second weight is just b2, etc. So this is the sort of final answer. The partial derivative of c with respect to w is just b1, b2, b3, and b4, which turns out to be just b transpose, the output of our hidden layer transposed, because remember we were representing that as a row before. So coding this up is just as simple as that. That's how much each weight affects the output of that layer of the network. And then, and notice also that this has the same dimensions as w. So in general, when you transform 4 dimensions into 1, you need a 4 by 1 matrix, 4 rows by 1 column. W is a 4 by 1 matrix. So this is the same dimensions as w, which is what we want. And now basically we can explicitly compute how much each of the weights affects the loss by multiplying those 3 partial derivatives we computed together. So basically this number here, negative 1.14, means if we increase that weight w sub 1,1 by 1 unit, then it would decrease our loss by 0.114 units. And so on, and the same thing is true for the rest of the numbers here. So we actually can explicitly compute how much we want to update our weights by. Pretty cool. So now that you have the basic idea, I'll go through the rest of these sort of partial derivative computations are similar. So I'll go through them a little more quickly and get to where we do the same thing basically for v. So we just computed this, the partial derivative of c with respect to w, and found that it was just b transpose. So a little bit of a tricky question, but we'll see if anybody can get this. What would the partial derivative, the next thing we want to compute is the partial derivative of c with respect to just b instead of w. So what would that be? If the partial derivative of this with respect to b instead of w. It turns out it's just w transpose. So you sort of switch the b and the w, and the math turns out to work out. Everyone just worked a day of work. It's like at ODSC, people were like enthused about data science, like yelling out answers, but everyone just worked a day of work. It's like 7 o'clock, you're ready to go home. I'll get to the cool stuff. So this turns out to just be w transpose. So that's cool. Coding that up ends up being easy. And so we continue to go backwards there. All right, next we want to compute this quantity. Turns out turning a into b was just the sigmoid function. So this is shorthand for, so because we already know how to do the derivative of the sigmoid function, that one's easy. It's just sigmoid of a times 1 minus the sigmoid of a. And we can code that up easily. And now we get to, and then we go back another step there. Now we get to the most involved of the partial derivatives, which I definitely won't walk through step by step. This one, it turns out, again, there's a linear algebra theorem that can make this a lot simpler, but I sort of go through it step by step here. In the same way that the partial derivative of c with respect to the weights w just turned out to be b transpose, the partial derivative of a, the input to the hidden layer, with respect to the first weight matrix v, turns out to just be x transpose. turns out to be our original data transposed. So this goes through exactly why that is. Just going through the equations, and basically I'll get to the main idea. The main idea is, remember, we're computing this. We're computing, there's a quantity A, and it changes by some amount as a function of each one of these 12 individual weights. So how much does each of those weights affect that quantity A? Well, it turns out you can show that that matrix of partial derivatives I just showed you turns out to basically be this, by similar logic to what we went through before. It turns out to just be x1, x2, x3, x1, x2, x3, x1, x2, x3, et cetera, where x1, x2, x3 are our original data points. And again, it's the idea that each one of those weights is only involved in certain parts of the equation that ends up transforming those weights into the next layer. So in terms of the matrix multiplication that results, you can just write it like that and code that up. All right. So we've gone all the way back. And finally, we can compute, actually sort of directly compute how much the loss is affected by each one of the individual weights V by just multiplying all those derivatives together. And it turns out this is the answer. So if you increase this first weight in the matrix, you decrease the loss by 0.02, and so on and so forth. And this has the same shape as V, which is what we want. Again, this works. It should work. We'll actually test and see whether it works in a second because of the chain rule from calculus. That's the only sort of math theory that's telling us why this should work. So now we can update the weights according to these equations. We just, by that logic we presented before, we just update the weights W. We just subtract off that dl dw quantity we computed. And for V, we do the same thing. And that's it. All right. Now let's put this all together. So by the way, and this is, if you're wondering like how you do a simple neural net from scratch, this is it in 20, 25 lines. This is just this is nothing new. This is just wrapping around what we just did. We have four things that take an input and make a prediction. We compute a loss. We do all these steps to get the backpropagation right, and then we update our weights. And there's our final, and then we return the weights. All right, now let's look at some results. So first of all, I'm going to train this neural net for 500 epochs. There's tons of terminology always thrown around with neural nets. So what's an epoch? An epoch is feeding all the data points in your training set through the neural net once. So what did I do? One epoch is I randomly pick a data point, feed it through the neural net. Randomly pick a different data point, feed it through the neural net, and do that with all 8 data points. Got 8 data points. Feeding all 8 through as one epoch. So I do that for 500 epochs. And this 4 here tells us to do 4 hidden neurons. So what actually happens? Well, it turns out this learns. It looks like it learns the relationship between these inputs X and Y. Let's actually check that it did. We've got our actuals there, and this is what the neural net is predicting the value of Y is for that input X. You'll see it actually works. Cool, it works on this toy example. That's fine. Let's check out if it can work on MNIST. Who here knows what the MNIST data set is? Cool, about half the room. So the MNIST data set is a famous data set of 70,000 handwritten digits. 7,000 digits, each 7,000 zeros, they're actually zeros, 7,001, 7,002, et cetera, all handwritten. So they're not, they're messy. And the task, and they're each 28 by 28, black and white. And so you have so each image is 28 times 28 features. So it's actually 784 features each of which has a value from 0 to 1. Each feature has a value from 0 to 1, which is how dark that pixel is, where if it's drawn in, that's a 1, and if it's completely light, that's a 0. So let's try to actually learn this problem, and I'll get into the specifics of how we're going to do it in a sec. Let's get the data from the sklearn library. I'm going to do a train test split here to make sure I'm not overfitting. 90% of my data I'm putting in the training set, 10% in the test set, just totally random. And that's that. Okay. Yep, train all. So let's check this out. So what am I doing here? I'm training this thing for one epoch. So first of all, I'm using the exact same neural net architecture that I came up with. And I call it neural net architecture because, again, it's just a series of equations. We don't even know if this is a neural net or can learn like a neural net. So it's a series of equations. It's the exact same equations, except now I have 784 inputs instead of 3. And I played around a little bit, and I'm using 50 hidden neurons. So instead of 4, I have 50. And for each prediction, I'm actually making 10 predictions. For every image, I'm predicting the probability that that image is a 0, the probability it's a 1, the probability it's a 2, etc. And then so I've got 784, 50, and 10 instead of 3, 4, and 1, but it's the same equations. And after training this for just one epoch, this thing can predict with about 93% accuracy whether an image is a 0, 1, 2, 3, 4, 5, or so on. So it's a pretty impressive result, and it just shows that, you know, with deep learning tricks and with using the latest techniques in TensorFlow, you can go find off-the-shelf code that you can just run yourself that can get above 99% accuracy, right? So you can do much better than this. But just coding the equations from scratch and training for one epoch and having a solid understanding of the fundamentals of how neural nets work, you can already get to 93% accuracy. So by all means, if you're doing neural nets in industry and you're trying to solve some cutting-edge problem, you should go learn the latest techniques. But it's also really important, I think, to have a solid understanding of the fundamentals, because again, the fundamentals already get you, 95% of the way there. All right. So that's just an illustration of like, neural nets aren't these big scary things. They're just a series of equations, and they work because of essentially the chain rule from calculus. And it's also true about complicated, long convolutional neural net architectures. All the matrix multiplications and everything that goes on during backpropagation is just to get the weight updates to line up in the correct way so that on every iteration, every single weight in the neural net gets updated according to that equation. It gets increased or decreased appropriately so that on the next iteration, the loss is slightly lower. And that weight update is computed using calculus. All right. So we didn't do any tricks here. We didn't even use deep learning yet. We just used simple neural net principles. Okay. Yeah. Yeah. There are a million tricks that you could look at. You could use different activation functions, different loss functions. I actually this was really a dumb approach in that I didn't even use a softmax. I didn't even normalize, in fact. So when I made these predictions on the MNIST data, to make this neural net better, what I could have done is just normalized my so I produce a vector of 10 predictions at the end. You could just divide that by the sum of the vector so that it adds up to 1. Like, I didn't even do that. I just fed this vector of 10 predictions, which could be 0.9 for every single prediction, and compared it with the actual. So there's a million things you could do to make this better, and I'll get into some of them in this talk. But yeah, the answer is yes. All of those things could work. Yeah, in the back. Yeah. How does it produce a step? Yeah. There are different activation functions that are a little more commonly used in cutting edge applications. ReLU, TANH, and there's a new one that's basically ReLU but with a curve at 0, which is ALU basically, or SELU. But yeah, there's a million different things you can do here. But again, I think it's important to understand the principle, which is that this is just a big mathematical function, and there's weights involved, and those weights are updated on each iteration using calculus. Yeah. Yeah, that's a great question. So I think it's important to note, even really deep neural net architectures are trained using backpropagation. This idea of, if there's one thing you come away from this talk with, it's neural nets are almost like a brute force approach. They're just try these architectures with a ton of different weights, update the weights a little bit each time, and hope that you get the right answer. And for many problem domains, they've been seen to work. If backpropagation fails, you try a different architecture and try a different weight initialization, and that's really what research is about. It's about figuring out which architectures work for which problems. Yeah, no problem. All right. So just to I think what we'll go through in the time we have left is how you get from this understanding of neural nets to deep learning. And essentially you do it by, if you think about the way we did that neural net thing, it was basically step by step, and there was some repetition in there. So there were a couple times where we fed something through we did a matrix multiplication and then fed something through a sigmoid function. And there were a few times when on the backpropagation we fed something through the derivative of the sigmoid function and then multiplied it by the transpose of the thing that it was multiplied by on the forward pass. And there was some repetition in there. And so you could think of neural nets, instead of thinking of it as a series of these individual functions, you could think of it as a series of layers. And each layer applies a certain set of functions to whatever it gets as input and feeds it on forward. And then it applies a certain set of functions to whatever it gets when it's doing backpropagation as sort of its output, and then sends it backwards in the neural net. And that's the sort of way you have to think about neural nets if you're doing deep learning. And as opposed to for the specifics of what goes on, to follow up on that idea of repetition, there's sort of this happening at every neuron in the neural net. There's a weight matrix on the forward pass, which is sort of the green arrows here. There's a weight matrix and there's input that's fed into this input, and then there's an activation function. And then when we go backwards, we do the derivative of the activation function, evaluate it at whatever the neuron input was, and then we have to feed it backwards to the previous layer by multiplying by the transpose of the weight matrix. So that thing sort of happened twice when we were going through that 2-layer neural net. So to sort of get rid of that repetition, we can think of neural nets as a series of layers that send values forwards and send, let me see if I can zoom in. There we go. That send values forwards and send sort of gradients backwards during the backwards pass. And yeah. First, I want to give props to this guy. This idea of coding the class structure that I use here to code up the neural nets from scratch come from this guy's GitHub. The actual sort of equations that go on, I sort of came up with, but this guy has an incredible GitHub with tons of examples of neural net stuff from scratch, and it's absolutely amazing. He's a student at the university. He was a student at a PhD student at a university in Denmark, and it's interesting. I was following his GitHub. I was reading his stuff. He was publishing papers, and then in early 2017, he stopped. He just went cold turkey. He stopped publishing anything on GitHub and stopped publishing any papers, and I just looked up to see what happened to him. And it turns out he started working at Apple as a machine learning engineer. So, people like him are the reason that your iPhone's really fast and can recognize faces and stuff. But yeah, his GitHub is amazing. All right. So there's some helper functions you have to use. So this is the basic way of you can think about neural nets if you're building deep learning from scratch. A neural net basically, okay, for the API that I'm going to use, we initialize it to have a list of hidden layers, each of which has the number of hidden neurons in that layer. So if I fed a neural net with hidden neurons being 50, 40, 30, 20, 10, that would be a neural net with 5 hidden layers, the first of which had 50 neurons, second of which had 40, then 30, then 20, then 10. I give it a number of outputs, I give it a loss function, etc. So when we do a forward pass on this neural net, we can set up the layers if we haven't done that already. That's straightforward. But this is the real fundamental way neural nets work. So each layer, no matter whether the layer is, in this case, they're all just fully connected layers. I'm using all the same kind of layer. But in other kinds of neural nets, they might be convolutional layers. They might be more advanced kinds of layers that do different transformations. But fundamentally, the layers are just doing the following. Or the neural net's doing the following. It's taking in your input X, and for each layer in the neural net, it's just feeding whatever that layer got as input forward in the neural net. And then whatever results from the last layer is your prediction. The next step is computing the loss, and you have some loss function that just takes in a prediction and your actual value y that you're aiming for in the neural net, and returns a value. And so I've got to zoom out here. And the backpropagation step is similar. Yeah, I'll get into that in a second. I see what you're saying. Yeah, that actually, I'll show you the way I code up the loss function in a second. So the backpropagation step is similar, basically. Every layer knows how to take whatever it got as a gradient and send it backwards. So it does some operations and then sends it backwards. And it does that the neural net does this in reverse order of whatever it did going forward, right? It starts with the layer closest to the output and sends whatever it got backwards. Let's run that. All right, so what's actually going on in these layers? Well, first of all, what does a layer have to do? It has to have a forward propagate function and a back propagate function. Okay, gotta do. Yep, went over that. Now, this part it's a little bit unavoidably messy. One way I could have made this simpler is coding the activation functions as their own layers. But to sort of transition from the way I did it in the first part, especially the backpropagation step gets a little messy. So I have some acronyms here. The layer input is LI. The activation input, what we feed into the activation function, is AI. The activation output is AO. And the layer gradient, whatever we get from the layer above, is LG. So, oh, did I skip that? There we go. So this is this is a way of abstracting away what we just did step by step. So this looks more complicated than what we did when we went through the neural net step by step, but it's really just taking those steps and abstracting them a little bit so that we could have a neural net that does the same thing as what we just did, but with 4 hidden layers or 5 hidden layers. So each layer has a number of neurons. It has an activation function. And for some stuff I do later in the notebook, we give it a number of iterations and et cetera. So when it gets a layer input, we sort of store that in the layer input there. But then it just does what we talked about during the step-by-step part. So first, we get this activation input. And what is the activation input? It's the dot product of whatever we got as the layer input times the weights. Right? We did that a few times when we were going forward. We did that twice when we were going forward. Took the dot product of the layer input and the weights. And then we fed that through an activation function. There it is. And we fed that through an activation function. And the backpropagation step is a little bit messy. So we get a gradient from the layer above. And if you remember, kind of like how we fed the sigmoid, when we were going forward in the neural net, The last thing we did in each layer was we fed things through the sigmoid function. When we go backwards, we fed things sort of through the sigmoid function, but the derivative of the sigmoid function, which was actually sigmoid times 1 minus sigmoid. So here's how we do that. We take the activation input, evaluate it at the activation function, but with this backprop flag set to true, which means evaluated at the derivative of the activation function, as you'll see. We get that quantity, and we multiply that by the layer gradient to get the derivative of the activation input with respect to the layer gradient, the thing we got from the layer above. Then, by that sort of matrix multiplication thing we went through, the derivative of the activation input with respect to the weights turns out to be the layer input transposed. And then the weight update is this quantity here, the layer input transposed, times the derivative of the layer gradient with respect to the activation input. And then we update the weights. And then we send the appropriate output gradient down to the layer below. Keep this thing going. So that's, again, it looks a little complicated when you write it up like that, but it's the same. It ends up coming down to the exact same steps that we went through before, just abstracted away a bit. And here's like how you would write your activation functions if you were going to do different activation functions. So the sigmoid function, you could basically say it does one thing when you're going forward, another thing when you're going backwards. If you're going backwards, do the sigmoid times 1 minus the sigmoid. And if you're going forwards, do that. And mean squared error, same kind of thing. If you're going forwards, just compute mean squared error. If you're going backwards, do this. Let's make sure we run those. Actually, I might have forgotten to run the prior cell. All right. And then you can just define a net like this. This is exactly what we did before, a neural net with 1 hidden layer and 10 outputs and a loss function of mean squared error. And just define some helper functions here. And we can, I won't even bother training that one for 1 epoch. You can basically, to show that these are actually learning, all the neural nets, basically this gets you consistently around 90% accuracy when you run this. Let's actually try, why not? Let's try a neural net with 3 hidden layers. I usually just show them with 2, but see if this actually works. Maybe with 3 it won't learn as well. With 2 it consistently gets around 90% accuracy, but with 3 we'll see what happens. No. The reason is deep learning models rarely overfit. That's not as much of a danger. The reason is doing computer vision is like a really complex problem. Taking in 784 values and determining what number something is extremely hard. Oh, it's only 72% accuracy when we do 3 hidden layers. So training this for 1 epoch with 3 hidden layers didn't actually do as well. But you can see that it did in fact learn. So this is in fact doing deep learning because it is learning. But it turns out with 3 hidden layers without doing any learning rate tuning or anything else, this doesn't learn so well for just 1 epoch. Before I get to the question in the back, so let's see. So it's 7:30. Basically, the rest of this is going through a bunch of tricks that people use to make deep learning models better. Tuning your learning rate, doing learning rate decay, varying learning rates by layer, momentum, dropout, all this kind of stuff. And we can go through as much of this as, we'll maybe go through just a couple of these, and then I'll like leave a bunch of time for questions at the end. But yeah. Actually, why don't I just speak to these? And I'll say that you can go through and look at the code of how to implement these from scratch and so on your own. So first, let's talk about learning rates. This is something that confuses a lot of people. A lot of people know at a high level learning rates are like, okay, if I have a higher learning rate, my net learns faster. And if I have a lower learning rate, it learns slower. But what's actually going on? What is a learning rate? So in terms of the framework we described, maybe show this part. Oh, and here's Yoshua Bengio, another, headshot. Yoshua Bengio, by the way, is the only, he's one of the, 5 or so leading neural net researchers in the world. He's the only one who has not left his post in academia and gone to work for either Facebook or Google. Every other one works for Facebook or Google. Jeffrey Hinton works for Google. Jan LeCun works for Facebook. Andrew Ng is also doing his own thing, actually. Andrew Ng is left and is doing his own thing. Oh, great. Cool. All right. I'll go a little slower then. Yeah. But yeah, Yoshua Bengio is still at the University of Montreal. Still just doing research. Yeah, Jan LeCun is at NYU, but he also works at Facebook, so I don't know what he spends more time. But yeah, he's really got it good. Okay, so what are learning rates actually? Learning rates are literally just a number that, now that we sort of know what's going on at fundamental mathematical level of neural nets, learning rates are just a number that you actually multiply that weight update by. So there's some stuff you have to do to code this up if you're doing this from scratch. Actually, learning rates are easy. Learning rates, you just multiply the weight update by a number. Yeah. Your learning rate? Yeah. That's the real answer for a lot of this stuff. You always get questions like, how do you choose your learning rate? How do you choose the number of hidden neurons, number of hidden layers, and so on? The real answer, honestly, is trial and error. It's people are trying different neural net architectures and sets of hyperparameters and seeing what works and what doesn't. I heard an analogy that I think is very unsatisfying to a lot of people, but I think is correct, and that's that humans discovered fire a long time before they knew the science of why rubbing 2 sticks together made flames. I think we're at that stage of neural net research right now. People have figured out that this stuff works, and they just don't understand why. Like, somebody asked me, the first time I gave this talk, somebody asked me, in the very simple example I went through at the beginning, where I have 8 data points, 3 features, 4 intermediate features, and so on, is there a mathematical guarantee that that will converge every time? If I run that thing for 500 epochs every time, will it actually result in a neural net that has learned the input-output relationship? And it strikes me intuitively that it should converge every time. And actually, I bet there is a mathematical way to look at the equations and figure that out. But I don't think there's a well-developed theory there that says whether it should converge every time. So the answer is I don't think people know the right learning rate. I think people are trying different learning rates and seeing what works. Yeah. I don't know, Luca, do you have any thoughts on that? Yeah. It's an art, yeah, which means it's guess and check. So here I go over, like, if you wanted to try different learning rates and see the accuracy of different learning rates, how you would do that. It turns out by doing that, I found out the best learning rate for sort of this architecture, doing image classification with gradients, the best learning rate was like 0.3. Yeah, let's talk about something else, which is varying learning rates by layer. So this is an important concept. One of the reasons that deep learning architecture I went through didn't work so well is that if you think about what we're doing when we're sending gradients backwards through a neural net, every time it's getting multiplied by, at most, the steepest derivative of the activation function. In the case of the sigmoid function, for example, that means that it's being multiplied by at most 0.25 at each layer. So in other words, the amount that you're changing the weight update by is getting smaller and smaller as you go back in the neural net. So it's like you're sending a fainter and fainter signal as you get far away from the actual loss. And this just illustrates, that's as steep as the sigmoid function gets. It only gets 0.25 steep. And so what you might want to do is you can actually, this is actually not sort of, this is a little unorthodox because technically this is no longer gradient descent. Because in gradient descent, you just multiply all your parameters by one learning rate. But what you can do is you can use different learning rates for different layers. You can use smaller learning rates for the layers that are closer to your output and larger learning rates as you go back. So that's what this does here. This shows like how you can actually do that from scratch. Actually, I'll show you in the setup layers helper function, basically. Oops. What happened? Yeah, in the setup layers helper function, basically, we go through the layers and we divide, as we go forward towards the output, we divide the learning rate by this learning rate layer decay parameter raised to some power. So if the learning rate decay parameter was 10, you'd be dividing the second learning rate by 10, dividing the third one by 100, et cetera. Yeah, there we go. Oops. Oh, I forgot to run one of the cells from before. That's okay. You can go through the code on your own. I promise it works. At ODSC, I had people running these cells and being like, wait, I tried a learning rate of this, and I got a better result. It's like the weights are randomly initialized, dude. I'm sorry. All right. Let's talk about momentum. This is a cool one. This is another one where you might have seen, okay, I should choose a momentum parameter of 0.9 or 0.5 or 0.1 when I'm training my learning rates, but I don't really know why. So what is momentum, actually? What's the idea? The idea is what we're doing with our updating our weights is equivalent to gradient descent. It's equivalent to saying, okay, we've got a ball and a hill, and the ball's rolling down the hill, and if, look at this point, the partial derivative of the point with respect to the blue line is positive, and we want to move this in the negative direction. So just like those equations we worked out before. But balls rolling down hills have momentum. So maybe our learning rates, maybe our weight updates should have momentum too. But what does that actually mean? Let's make that a little more precise. So let's say that our weight update at time t was u sub t. If we had momentum in our weight updates, then our weight update at time t would be u sub t plus a momentum parameter times whatever the weight update was last time, times the momentum parameter squared times whatever the weight update was 2 time steps before, et cetera. And mu is just a decay parameter between 0 and 1. And this is equivalent to, and often described as, increasing your learning rate when their weight updates are going in the same direction, and decreasing your learning rate when your weight updates are zigzagging. And coding this up, so you just add a momentum parameter to each layer. And it turns out to be simpler than you might think. So the way you code this up, you don't have to code a long series of like some infinite sum. What you do is you say, you initially set your velocity equal to what the weight update would be normally. So your learning rate times your weight update current here. Then on each iteration, what you do is you add the momentum parameter times basically the sum of all the prior weight updates plus the current weight update. So it starts out like u sub t. Then it's the momentum parameter times u sub t minus 1 plus u sub t. Then it's the momentum parameter times all of that plus the current weight update, et cetera. And so coding this up is just you take at every step, you just take the momentum parameter, multiply it by whatever all the weight updates prior were, and then add the current weight update. I think that's actually the most interesting one from a coding perspective. And you can test this out. If you do this from scratch, or if you use a library like Keras or TensorFlow, you can test out different momentum parameters and see what ends up making the neural net learn better. All right, dropout. This is an important one to know. So dropout is a technique that has been shown to make neural nets train better in a lot of cases. And I think a good analogy to understand dropout is this. Let's say you're a basketball coach and you have a team of 10 players. During the regular season, you might do the following. You might say, in every game, I'm only going to have 8 players available to be put on the court. Doing so is going to force my players to learn to play together in different ways. It's going to force us not to be reliant on one star player. It's going to force us to come up with new strategies and so on. That's essentially what dropout has been shown to do. it turns out when you don't apply dropout, what can happen is that a few neurons or a few weights can dominate a neural net's prediction. And when you take those out of net on certain classes, the net ends up learning sort of redundant representations of whatever the underlying thing is it's trying to predict. So what do you actually do in Dropout? What you do is, so remember, neural nets are a series of layers sending info forward. Right before you send the info onto the next layer, you do the following. You say, I'm going to select 20%, 50%, some proportion of my neurons, my values, and set them equal to 0. And then I'm going to send that forward to the next layer. And that turns out to, when you randomly select a different 20% or 50% on every iteration, it turns out to actually make the neural net learn better overall. Coding it up turns out to not be that interesting. You just take half the neurons and set them equal to 0. So I guess a couple last quick ones, and then I'll stick around and answer questions as long as you guys want. Weight initialization. So there's something called Javier or Javier weight initialization. I'm not sure exactly how you pronounce it. I should ask an actual expert in this at some point. The idea is this. Initially, we initialized our weights to all have, say, mean 0, standard deviation 1, and be drawn from a normal distribution. If we sent that forward to the next layer, the layers that had, so every neuron in every layer is a linear combination by default of all the neurons in the prior layer. So if we send all those weight updates, all those weights that have been each drawn from a normal distribution of, say, standard deviation 1 forward to the next layer, that neuron in the next layer is going to have a variance that's proportional to the number of neurons it received. And so if we want each layer to sort of get the same variance from the prior layer, what we can do is we can scale the standard deviation that we draw our weights from by the inverse of the number of neurons. So you set the standard deviation of the normal distribution you're drawing your weights from to 1 over n, where n is the number of neurons in your layer. And this has been something that's been shown to work very well in practice and has the sort of theoretical justification that I just provided. So how you do that is actually pretty easy. You just take your weights and you scale them by the number of neurons. And you can code this up. The rest of it's pretty straightforward. Then drop connect. This is kind of an interesting one. It turns out still the architecture that has been shown to get the highest performance on MNIST uses this technique called drop connect. This technique hasn't been shown to work extremely well, or at least hasn't been tried a lot in other computer vision or other problems, but it's available. It's not in TensorFlow, but if you do this from scratch, you can easily implement drop connect. All drop connect is, it's the same idea as dropout, except before you do the multiplication of your input to your layer with your weights, you randomly set some portion of your weights to 0. So same idea as dropout. You force your neural net to learn redundant representations of your data and not be too reliant on certain weights. It worked really well for one team of people in the MNIST problem. And it's cool that once you understand this stuff at a fundamental level, you can actually see how you can play around with all sorts of techniques like this and when you're coding things up from scratch. Again, actually coding this up turns out to be not that interesting. You make sure all the right attributes are added to the right classes, and then just randomly select some portion of the weights and set them equal to 0. You're just going to have to trust me, or you can try on your own, that if you run all this code, it will actually work. All right. That's all I've got. So thanks, everyone, for listening. I'll stick around as long as you guys want for questions. Feel free to, we can just do an open Q&A. You guys can just come up and ask me. Go get pizza if you want. Yeah. Cool. Thanks for coming, everybody. Come on up. Yeah. Or don't. Yeah. Or we can do it this way. Either way. A little bit. His question was about specifically sequence-to-sequence models and coverage and attention. A little bit. So sequence-to-sequence models are the state of the art in language translation in particular. That's the problem they were designed to solve. So they take in a sequence of inputs and produce a sequence of outputs. I supervised a student who was working on a project in our last boot camp who did an article summarizer, and it actually turned out extremely good. She found an architecture based on, implemented in TensorFlow, based on a recent Google paper, and she fed her data through that and was able to get and train from scratch an article summarizer that took in an article and produced a summary. It was trained on actual articles and summaries. And yeah, that had attention in it, as well as being a sequence-to-sequence architecture. I think as with any of these architectures, I endeavor to fully understand how they work, but I can't claim to. I think I understand how the basic neural nets work, and I'm getting there on convolutions and RNNs, but yeah, there's a lot of new techniques being produced all the time. So, yeah. No, Siamese networks, I've heard that term thrown around, but I'm not familiar. Yeah, often a thing to, yeah. Yeah, his question, Luca's question was about hardware. So as you've now seen, doing both the forward and backward passes of neural nets, doing them efficiently happens to involve a lot of matrix multiplications. Again, that's not because there's any linear algebra theory involved. It's just an efficient way of expressing that the outputs or the inputs to the next layer are linear combinations of the prior layer. So people have used GPUs basically, which are specialized computers for specialized chips that do matrix multiplications extremely fast. Or they're really specialized for doing parallel computations very fast. And matrix multiplications, as it turns out, are sort of infinitely parallelizable. So GPUs are used to train neural nets. How do you get a GPU? Turns out Apple doesn't make great GPUs on its computers, but you can basically rent them on AWS. You can rent state-of-the-art GPUs, and if you're comfortable working in a Linux environment, you can spin up an AWS EC2 instance, Elastic Compute Cloud, and clone a GitHub repo onto there, or even use a pre-made thing that already has the GitHub repo on there, and start playing with neural nets pretty easily. Yeah, I think it's definitely increasingly essential to be familiar with AWS EC2 and Docker and GitHub to be able to even get started with this stuff. Or it's more like if you want to get started very quickly, then knowing that stuff helps a lot. Yeah. Yeah. Yep. I'm sure you could use other techniques. Yeah, the backpropagation algorithm, what I just showed was the backpropagation algorithm. You know, and I think very close variants to that are what are used even in cutting edge applications. Because again, the principle of getting the weights to change in the right direction is still the same. But yeah, maybe you could, there might be other similar techniques as well. Yeah. 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 Actually, I'll go to you since you haven't asked a question yet. How do they use what? Oh, yeah. Yeah. The thought has traditionally been you need lots of training data to do neural networks, and if you don't have lots of training data, you should use a simpler algorithm. people are now coming up with, how do people come up with those rules of thumb? I think it's just trial and error, seeing that training neural nets with smaller data sets doesn't work as well. Cutting edge area of neural net research is, so it turns out there are things called generative adversarial networks, or just generative models in general. It turns out if you can set up neural net architectures that can take in a bunch of images of digits and generate new images of digits. And essentially you can use a neural net both looking at actual images of digits while also learning to distinguish between real images of digits and fake images of digits to train neural nets with a lot less training data than you traditionally need. For really complicated things like street view house numbers that Google needs or other things like that, you can't get as close to the cutting edge as you can with just tons of training data, but you can get really far nowadays with little training data using this generative idea, and that's called semi-supervised learning. So, yeah. Transfer learning, yes, is another thing people are using, and that's sort of a totally separate thing. But transfer learning is, so neural nets have many layers. For neural nets relating to images in particular, convolutional neural nets, the first layers of the neural net learn general features about what distinguishes one image from another. Like, are there lines in the image? Are there curves? Are there certain colors in certain places? And the later layers of the neural net, as it turns out, once they're trained, actually distinguish between the particular classes that you're training on. So those will actually figure out which combination of the general features tells you that an image is of a cat or tells you that an image is of a dog. So what people have figured out they can do is they can take the first 80% of the layers of a neural net and transfer them over to another neural net and then just train the last 20% of layers using their data set to get essentially cutting edge results with less data and less training time. That's a 30-second explanation of transfer learning. But so yes, it's similar to semi-supervised learning and probably more widely used in that it's another way to get more horsepower out of little training data.